Today we want to talk about how we would prepare a buffer solution. And when I prepare or when I do problems that involve preparing buffer solutions, I like to use something called the Henderson-Hasselbalch equation. The Henderson-Hasselbalch equation looks like this for an acid, looks like this for a base. And if we want a pH, a buffer of a specific pH, we're going to use the equation that takes the negative log of the equilibrium constant plus the log of the concentration of the salt ion that is part of the weak acid and the weak acid. Likewise, if we're dealing with a base, the pOH, desired pOH, is going to be the pKb, which is the negative log of the equilibrium constant for the base, plus the log of the salt ion that's part of the base and that weak base. So that's the equation that you're going to be using. So let's look at our first example. Our first example says that we want to prepare a buffer solution that has a pH of 5.30, and we're going to make it from propionic acid and sodium propionate. And the concentration of that sodium propionate must be 0.50 moles per liter. What should be the concentration of the acid in order for this to work? And it gives us the Ka for the propionic acid. Now that's very nice because you might not have known what the formula for propionic acid was. Now you do. So once we know we're making a buffer solution, we're going to use Henderson-Hasselbalch, and it's an acid, so we're going to use the pH equal to pKa plus the log of the salt ion over the concentration of the weak acid. It told us that the pH was going to be 5.30. That's what we want it to be. pKa, we're taking the negative log of the equilibrium constant, which it nicely gave us at 1.3 times 10 to the minus fifth. And we're going to take the log of the salt ion, which is what they gave us the concentration of. They gave us the concentration of sodium propionate. Remember, if it's Na and some ion after it, that's your salt. Metal plus something that's acting as a nonmetal. So that's the concentration of your salt ion. And we're trying to find the concentration of the acid that we need. So working some of this out, 5.30, we know the negative log of 1.3 times 10 to the minus fifth after we plug it in our calculator is 4.886. And again, we're going to be doing the log of 0.50 over concentration of, in this case, our HA. I could go ahead and put in propionic acid there, but I'm just going to keep HA. It's much quicker to write. I know at the end that what I'm finding is the concentration of this acid right here. So now what I want to do is to subtract 4.886 from both sides. And I end up with 0.414 on this side. Of course, it drops out on this side, equal to the log of 0.5 over concentration of HA. And now I've got to solve for something that's part of a log term. Now we've done something like this before. We've done it when we were dealing with natural log, ln. We took inverse natural log of both sides. Well, this time we're going to take inverse log of both sides. Inverse log of both sides is going to cancel the log term on this side. And inverse log, and I don't know any other way for you to do this, but to memorize it, simply means we're going to take 10 and raise it to the power of the 0.414. So that's what we mean by inverse log of that number. So 10 raised to the power of 0.414 is going to be equal to 0.50 over the concentration of HA, since I dropped out that log term. That is 2.594 once we find 10 raised to the power of 0.414, still 0.50 over concentration of HA. And solving for this, remember, we're going to flip places with this, okay? Please be careful because people are constantly solving this wrong. They'll say that HA is equal to 2.594 over 0.5. It's exactly the opposite. Flip-flop these two for a shortcut. I know math teachers hate it when I do that, but HA is going to be equal to 0.50 over 2.594. Doesn't look much like a 5, but it's supposed to be 2.594, which gives us a value of 0.19 molar. And remember, now we know it's CH3. It's got a little CH2 in between it. It's close to being the same formula as acetic acid. It's just got a little CH2 stuck in there, an extra one. So this is the concentration that we need that acid to be in order to get this buffer to 5.30 pH. Another type of problem you might see might be one like this. It says you wish to prepare a buffer to maintain the pH of a solution at 4.30. There's a list of possible acids here in this table and their conjugate base or their salt ion. And it gives the Ka values. And again, we want this to be buffered to a solution of 4.30. And we kind of mentioned this earlier when we were talking about how we want the pKa to be close to the pH of the solution that we want it buffered. Since we want the pH to be 4.30, we want this log to be as close as possible to that value. And the one that's as close as possible to that value is the 1.8 times 10 to the minus fifth. So we're going to use the CH3COOH system since it has a pKa closest to 4.3. So we're going to choose the CH3COOH system with the CH3COO, acetic acid and its salt, because the pKa is approximately equal to the pH, and that's what we want it to be. Finally, which combination, after we select this, which combination is selected, what should be the ratio of acid to the conjugate base? So we're dealing with a buffer. Let's look at our equation again. pH equals pKa plus the log of the salt ion over the acid. I like to write A minus and HA. I know we're dealing with CH3COO minus and with CH3COOH. That's a whole lot quicker to write this way. So we want this to be 4.30. The pKa of our acid, if we take the negative log of this value right here, we get 4.745. which is what we're going to put in down here in our problem. 4.745 for our pKa plus the log of this quantity, A minus over HA. Now we're going to subtract 4.745 from both sides. Of course, it's going to cancel it over here, and we're going to get negative 0.445 here is equal to the log of this value. Now we want to take the inverse log of both sides to solve for that. So we're going to take the inverse log of this side. Now let me do that in a different color so it doesn't start all just kind of blending together. And the inverse log of this side. So inverse log cancels here with that log, so that term drops out. Remember, this becomes 10 to the negative 0.445 is going to be equal to A minus concentration over our HA. Move this down a little bit so I have a little more room to write. That number value becomes 0.359. Now, this is where how it's stated in the problem becomes very important. The problem asks for the ratio of the acid to the conjugate base or salt. Look at what I've got now. Right now I've got conjugate base or the salt over the acid. So what I need to do is to flip-flop that to get that ratio the way it's stated in the problem. So if I want to do that, I need to say that HA is on the top and A minus is on the bottom. I want a ratio of acid to salt. And that's the way it's phrased. Acid to salt means acid's on the top, salt's on the bottom. And if I'm going to flip-flop those, I better take the inverse of this, right? So 1 over 0.359 which is 2.8. And I don't want to give anybody a reason to not give me credit for this, so I'm going to state it just like the problem did. The concentration of CH3COOH to the concentration of the salt ion, the acetate ion, is equal to 2.8 to 1. Changing those fractions into a fraction form into a ratio form like this. So that's how I would write it, just to make sure no one has any choice but to give me full credit for this problem.